All right, so this is part three. We're going to talk about water, properties of water, acids, bases, pH. So let's start with the properties of water. So water, why is water so special? Everything, all life on the planet Earth is water-based. There has to be water involved in anything that's alive. Inside of every cell, the interior is mostly water. So you probably heard that our bodies are mostly water, and this is true. Okay, because every single one of our cells is filled with water. The chemical reactions that go on in our cells are dissolved in water. So water is very, very, very important. So here are some properties of water that make it special. Number one is cohesion. So cohesion is the ability of water to stick to each other. Why do water molecules stick to each other? Well, we just talked about that. It's because of the hydrogen bonds that form between water. If you have a lot of water, it's sticky. They stick to each other because of hydrogen bonding. Okay, so water molecules can stick to each other. What that does is funny because when water in the pond, let's say, right underneath the surface, it's very fluid. But at the surface, you don't have any more water. You have water here, but then air. When you have a break in water, water will organize itself very more organized in a more organized way, I should say, than beneath the surface. And what that creates is a surface of water that is kind of thick and it has something called high surface tension. It's a little bit hard to break the surface of water. This is not true in alcohol. If you had a glass of water and a glass of vodka, I'm not condoning that, but the surface of those two different liquids will be very different. And water has this high surface tension. So because it has a high surface tension, it is a great area for organisms to use as a habitat. So there are insects, there's actually some, I think some lizards or larger animals that can actually use the surface of water to hunt on, to walk on. So it's good for biology, for the diversity of life, to have something, the high surface tension here. The next property of water is adhesion. So adhesion is the ability of water to attach to other things. So in this picture, right, water is sticking to the sides of maybe a small little tube, and cohesion is the water sticking to each other. So this is a great picture showing you adhesion and cohesion. Because of adhesion, there's something called capillary action. So I'll also put this in the module for you guys to watch. Capillary action is the ability for water to move up a very small tube without any help. So think about, I think this is what the video is, if my memory serves correctly. If you've gotten your blood taken to test for anemia, and they'll take a very small glass tube and they'll put it onto the drop of water, and the drop of blood, the drop of blood will get sucked into that tube without any help. Why did blood just run up that tube? It's because of something called capillary action, because your blood is mostly water. Water likes to stick to the sides of things. If this water molecule stuck to the side of the wall, it's going to bring along other water molecules because it's sticky, because of cohesion. And then this is slowly just going to creep up the this small little tube. Capillary action is important and significant because this is how trees and other large plants will get water from the surface all the way up to the top of their very, very topmost leaf. Think about those like 100, 200 foot tall redwood trees, right? They're getting water from the ground. So how is water moving up their body, right? If you call a tree the whole organism, the body, how is it moving up? It doesn't have a pump. There's no heart, right? So there is this mechanism that evolution has used because water has this adhesive property. So it creates this capillary action, which allows these larger plants to grow. Pretty cool. All right, let's look at the next one, which is the high heat capacity. It has a high heat capacity. What that means is that water can absorb a lot of heat or release, I should actually put, or release a lot of heat without changing temperature. So if you put on a pot of water to make pasta, which gets hot first, the metal pot or the water? obviously the metal pot, right? The metal pot has a low heat capacity. It can, a little bit of heat exposure to that metal, and the metal immediately changes temperature. It doesn't have any capacity to um, remain at the same temperature. But water does. Water has a high heat capacity, meaning it can take a lot of heat, not change temperature yet, right? So you have to wait a very, very long time for that water to boil because the water's resisting changing temperature. The same is true in the opposite way. It can cool down, so it can release a lot of heat also without without changing the temperature. This is great for biological systems, for living things, because water, which we are all mostly made of, right? Plants, animals, all living things are mostly water. If water changed temperature very quickly, then things would boil, life in the water, aquatic life, would either boil or freeze very easily, and that's not conducive for life. It also means that the climate, so if you live close to a beach, if you think about the weather in Santa Monica or in Malibu, it's always the same. It's never this huge fluctuation because the ocean can absorb a lot of heat on a hot day and it can donate heat. It sort of exude the heat on a cold day. So the water can mediate the heat. And then if you compare that to the desert where there's no water around, in Joshua Tree, if you've ever been to the desert, it can be really hot when the sun is out, like 90, 100 degrees, and then freezing cold when the sun goes down because there's nothing to mitigate the heat or trap the heat during the day and then expel it at the nighttime when it's cold. So areas around a large body of water, the climate there is going to be relatively constant. If you're not near a body of water, it's going to be very variable depending on whether the sun is out. And then another implication of this high heat capacity is evaporative cooling. We cool ourselves with the water in our sweat. Well, how does that work? So when you sweat, there's water on your skin. Your body is very hot. So that water is going to absorb the body's heat. It's going to take the heat out of your skin. It's going to pull it into the water itself, into the sweat. Eventually, that bead of sweat is going to get so hot, it's going to evaporate, right? Because that's what happens to water. When water picks up heat, it turns into a gas, right? So when you evaporate the sweat from your body, you're taking all the heat from the body away with it. So that's how we cool down, evaporative cooling, okay? Our humans have evolved sweat glands on the skin for this purpose only, okay, evaporative cooling. Here's an example of a lot of evaporation happening, right? All right, so let's look at the universal solvent, which is letter D in your outline. So we talked about how water is polar and it can dissolve anything else that's polar. Turns out there's a lot of polar things in the world, and so we call water the universal solvent. It can dissolve almost anything. That's polar. Okay, so let's get some definitions straight. Solvent is something that does the dissolving. In biology, the solvent is always water, okay? Solute is something that is dissolved. So if I'm making a glass of Kool-Aid, what's my solute? It's the Kool-Aid pack. What's my solvent? It's the water. And the solution is an even mix of the two, right? I have a solution of Kool-Aid. It's a completely homogeneous. What homogeneous means is it's not, you don't have like a pile of Kool-Aid at the bottom. It's like evenly mixed. Okay, and then the word aqueous solution, aqueous means water, so it's just a solution that has water as its solvent. So anything we talk about in biology class will be an aqueous solution. All right, so, and then coming back to the last one, the lower density of ice, oops, sorry. This is my slide on the lower density of ice. So water, when it is a liquid, the shape and the hydrogen bonds that it has is tighter. It's a smaller molecule and you can fit more water molecules within a certain area. And so this is how liquid water, it's making and breaking hydrogen bonds. When water freezes and becomes a solid, what happens is the molecules no longer move around. So what makes a liquid is that the molecules are moving past each other. That's a liquid. A solid, the molecules are not moving past each other, they're stuck in place. So when water freezes, what happens is you can see how less dense, how much fewer water molecules we have here than here. When water freezes, it grows in size a little bit and the hydrogen bonds get bigger and longer. So you can't fit as many water molecules in the same area as you can when you had water. And so when it gets stuck this way, when it's frozen, there's more space and that makes it less dense. It also causes it to expand. I know that we've all probably put something in the freezer, like a bottle of water, a plastic bottle of water, or maybe a can of soda into the freezer, and then you forget about it. And when you come back to it, it's exploded, right? Because it expanded, the water in your drink expanded as it froze, and it created a less dense solid. This is very unique to water. Other liquids out there, when they become a solid, they get denser, they get more compact, but water's the opposite. Water gets more air trapped inside, it's less dense. So how is this good for life? Because oceans and lakes don't freeze solid. So you think about oceans and lakes, when it's very, very cold in winter, the top will freeze. That ice never sinks down to the bottom of the ocean because ice floats. Let's just do a thought experiment and think about what happens if ice actually did sink. So ice would form at the top because that's very cold. It would sink down to the bottom and you'd have a layer of ice at the bottom. It would never melt because the bottom of an ocean or the bottom of a lake would remain cold. The next winter comes around, it happens again. So what would happen is that over time, the bottom portion of an ocean or a lake would be constantly frozen. And so this does not lead to a lot of diversity in terms of what you would find living in an ocean or a lake because the bottom is just gone. And so that's good. So because the ice melts and freezes and is always just at the top, you can have more diverse aquatic life. All right. So we talked about that. So what is a property of water? Your answer should be letter D. The solid form is less dense than liquid form. Okay, let's talk about our next topic, acids and bases. So I want you to write down the definition for letter B and C when we get there, but let's first talk about water. So here are two molecules of water, and what is between our oxygen and our hydrogen? This is a hydrogen bond. Every once in a while, and this is just what happens, a hydrogen will pop off one of the water molecules and move over to the other one. Okay, so this is what's showing you what happened. When this happens, you get an H3O, which is called an hydronium ion, that has an extra positive charge because what happens is the electron stays here and the proton of hydrogen moves over. So this one gets an extra positive charge. This one remains with a negative charge. So then you get a hydroxide ion. So OH negative is hydroxide ion. H3O positive is hydronium ion. Now I'm going to, in your notes, it's also written that this H3O is just H2O, but what's extra? It's the H plus that's extra, right? So we're going to just abbreviate hydronium ion to H plus because we can ignore the H2O there. So this is H plus. Does that make sense? Hopefully that makes sense. So if you had only water and this happened, right, the dissociation, so the hydrogen ion comes off, the hydrogen atom comes off and goes to the other water molecule, that's called dissociation. This is what you're looking at, dissociation. What is created when you have dissociation of water? You have one hydrogen ion made and one hydroxide ion made, right? You're always going to have one of each because when the hydrogen atom moves over, you get this and this, all right? So hopefully you understand that every time dissociation happens, you have an even formation of a hydrogen ion and a hydroxide ion. In pure water, right? This would happen. You have an equal number of hydrogen and hydroxide, and that's the definition of a neutral solution. So now we're talking acids and bases and neutral solutions, right? So what does it really mean to be a neutral solution? It means that you have an even number, the same concentration of hydrogen ions as you do hydroxide ions, okay? So then what would change that? A change in the number of hydrogen ions or hydroxide ions would be where acids and bases come in. So what could cause an aqueous solution to have an imbalance of hydrogen ions or hydroxide ions? Now you need to add different things to water. We can't be dealing with pure water anymore. An acid is a substance that will add more free hydrogen ions to a solution. And that's the definition of an acid. An acid has more free hydrogen ions. So something like HCl, this is hydrochloric acid. When you put HCl into water, then the H and the Cl's break apart, and then look what happens. We don't care about the Cl's. Just ignore that. We only care about H pluses. We are having more H pluses in that water because we added HCl to the water. So now the water is acidic. It has more H pluses in it, right? Hydrogen ions. A base does the opposite. A base is a substance that will add more hydroxide ions to a solution, or it can do another thing, or it can sop up, it can take away or reduce the free hydrogen ion concentration. So something like sodium, well, actually look at ammonia. So NH3, if you put that in water, it will suck up any extra H pluses to make NH4. But what you're doing is reducing the H pluses, and that is going to be less acidic, right, or more basic. Sodium hydroxide, this one, NaOH, if you dump that into water, the Na and the OH separate, and you're adding OHs to the water. You're adding hydroxide ions. So you're also, that's a base, right? You're adding more hydroxide. So let me show you actually this picture, right? This is from your textbook. So this is a neutral solution. This is where you have 1, 2, 3, 4 hydroxide ions in black. You have 1, 2, 3, 4 hydrogen ions in pink. They're even. They have the same amount of each, so that's neutral. This nomenclature here, how this is written, this is also in your notes. The brackets mean concentration of. So how you read this is the concentration of hydrogen ions equals the concentration of hydroxide ions. Okay, so that's some chemistry there. As you go, let's go acidic. As you go in this direction down the pH scale, look what's going on in your water. You have more hydrogen ions than you have hydroxide ions. So you have an imbalance, but it favors hydrogen ions. The more hydrogen ions you have, the more acidic your solution will be, and the number goes down. So number 7 is a neutral pH number. As you go to 6, 5, 4, 3, 2, 1, 0, yes, the pH scale goes to 0. This is more and more and more acidic. So and I'll talk about that in just a second. But if you go up the opposite direction where you have more hydroxide ions in that water than hydrogen ions, you have an imbalance here that favors hydroxides, then that solution becomes more and more basic, or you can use the word alkaline, okay, alkaline. So you can see that different substances here, you can take the pH of different substances and they have different numbers based on their pH. So an interesting thing for letter D, pH stands for the power of hydrogen, because really what you're looking at, these free hydrogen ions. The more you have, the more acidic it is. The less you have, the more basic it is, okay? So the pH scale is from 0 to 14. 0 being the most acidic, 7 in the middle for neutral, and 14 for the most alkaline or basic. So let's look at this. pH scale. What does pH stand for? That's in your notes. It's the power of hydrogen. So the scale is logarithmic. This means that every number is a 10 times difference in how much hydrogen ions are present or how much hydroxide ions are present. tenfold. So this is kind of like the way the um, earthquake scale works, okay, the Richter scale. A earthquake of 2 is 10 times bigger than an earthquake of 1. Okay, so this is the same way this works. So how much more acidic is lemon juice from bananas? So let's go to our scale here. Oh, here's the acids. So here's lemon juice. Lemon juice is 2. Where's bananas? Bananas is 5. So 2 to 5. So from 3, let's just move from 2 to 3. So from 2 to 3, we know the 2 to 3 is 10 times difference. From 3 to 4 is another 10 times difference. From 4 to 5 is another 10 times difference. So we have 10 times 10 times 10. So the answer is 1,000, okay? Not 3, not 30, not 100, 1,000. So every time you move up, you multiply a 10. Multiply the 10 or divide the 10, okay? So that is that. So hopefully you guys can, what I want you to get from pHs is know what an acid and what a base is. You can also use your textbook to find those definitions. You know what the pH scale from 0 to 14 and know how to answer a question such as this, right? If one is, compare the how much more alkaline is ammonia than baking soda? If I ask you that question, ammonia to milk of magnesia is 10. 10 to 9 is another 10. So we have two 10s. 10 times 10 is 100, right? So we would say ammonia is 100 times more basic than baking soda. All right, so let's look at our next topic, which is a buffer. Buffers are extremely important. Buffers are chemicals. So I'm going to read from your outline. It's a solution that resists change in pH when acid or alkali, which is a base, is added to it. Buffers are molecules that can bind a free hydrogen ion or release one to ensure the balance of hydrogen ions maintains a consistent range. So let's take a look at our example here. Our blood has a buffer, and I have the example in your notes. It's carbonic acid. It's carbonic acid / bicarbonate, but anyways, it's we have a buffer in our bloodstream because if you were to drink lemonade, right? So our question, let's go back to the question. What happens to our biological fluids and blood when we drink something that's lots of acids in it, like soda or lemonade that has a pH of 3? So if you drink lemonade and you are drinking a glass that has a pH of 3, your blood has a pH of 7.4. What's going to happen to the pH of your blood? Is it going to go down because you're just dumping a bunch of acid into your body? No, it doesn't. It remains at 7.4. Why? Because we have a buffer in our blood. The buffer, so let's go back here, right? Think. What is happening when you're drinking something that's acidic? You are putting more hydrogen ions in your body. A buffer can act like a sponge and suck up those extra hydrogen ions so the pH doesn't change. The opposite is true as well. So if your blood becomes basic, your carbonic acid can donate hydrogen ions to the solution. So buffers minimize changes. Okay. You will die if your blood reaches a pH of 7 or 7.8. So even a seemingly small change in pH can be very deadly for us. So buffers are very, very important for living things. Okay. Why does pH matter? That's a good question, right? Why does the pH matter to living things? Let's take a look here. We would never drink battery acid. It has a pH of 1, but we would drink lemon juice. It's only 10 times difference, but battery acid is, so why does such a strong acid bad for us, right? Or you would never drink oven cleaner. You'd die if you drank bleach and oven cleaner, right? So why is this solution so bad for us, and why is this solution so bad for us? Well, it turns out that our molecules and our cells and everything that's inside of our body, everything we're made of, is made in a certain pH range. And once you start changing the environment that your molecules are in, those extra ions can, you know how they have a negative charge? They can start pulling apart the bonds that exist in your normal molecules because your molecules are not used to having extra negative charges or extra positive charges around. So if you start adding a whole bunch of negative charges to your blood or to your skin, right, it starts to dissolve and ruin and just destroy those molecules. So if you destroy your molecules, nothing works. You end up dying. Okay, so it's really important that we maintain a pH range that's compatible with what chemical reactions are happening inside of our bodies. They evolved over, long thousands and thousands, hundreds of thousands of years to work really well at a very specific pH. If you change that pH, you change the environment that those molecules are working in, they're not going to work. Okay, so that's why pH matters. And just on a very basic level, you will buy soaps or, shampoos and lotions, and sometimes they say they're pH balanced. Well, of course they're pH balanced because it'll burn you or dissolve your skin if it's not pH balanced. So the fact that they're saying they're pH balanced, that's like bragging that you're breathing. Like, of course, you would have to, you have to balance the pH if you're going to sell a product that goes on somebody that's alive. Okay. You don't want to kill them. Okay, so that's buffers. So soda generally has a pH of 3. This means that soda is, and I hope you said acidic, because anything smaller than 7 is an acid on the pH scale. All right, and that's it.